One final definition in this section, section 16.2, is that of flux. So let me draw a picture to illustrate what flux is. So the first thing that we need is that we need some kind of curve, and we're going to assume everything here is just in the plane. It's going to be a simple closed curve. It doesn't cross itself. It starts and ends, so it's a single loop here. And let's just suppose that things are oriented counterclockwise like this. And then suppose, so this is our curve C. Suppose that we have some vector field here. Let's say that we have some vector field F. And let's suppose that this vector field F corresponds to some flow of some object. So like, for example, this could be water flow. I drew in blue, so it could be water flow. I've seen people interpret flux about like animals and stuff like that. Like you have animals moving around, and so the vector field corresponds to the movement of animals, the flow of animals. What we'd like to do is have the question answered: how much of the quantity, how much of whatever is water, animals, whatever you could think about, is flowing into the region inside of here versus flowing outside? So the question here is, how much flow is leaving the region? Let me say this region here is R versus entering. And and how can we precisely quantify how much is leaving and how much is entering? And so the idea is that in order to do this, we're going to think about taking the dot product of, oops, that's not a very good arrow here. Okay, what am I drawing? I need to say what I'm drawing here. What I'm drawing are outward pointing normal vectors. So the dot product of the dot product of our vector field F with the outward pointing normal vectors will tell us at the points along the boundary here how much of the fluid flow or whatever it is moving outside of the region R versus moving inside the region. And the stuff is moving parallel. That if something is moving parallel with our boundary, that's nothing to do with leaving versus entering. It's just moving along. We want to emphasize leaving versus entering. So this is the big picture for what's going on here. Here's our formal definition. If C is a smooth, simple closed curve in the domain of a continuous vector field F, where to m of xy times I hat plus n of xy times j hat in the plane, and the n hat is the outward pointing unit normal vector on C. And the flux of F across C is the integral over C, and let me put a loop here to say, hey, it's a closed loop of F dot n ds. And the interpretations here, because we're having an outward pointing normal vector with dot products, is that assuming we're orienting things counterclockwise, which we really should be doing, if flux is positive, that corresponds to net outward flow. If flux is negative, that corresponds to net inward flow. Okay, so this is our definition of flux based off of the drawings that we had. This wouldn't be very useful to compute with, so after some details I'm skipping over here, here's our formula for how we actually compute flux across a smooth closed plane surface. The flux of F, and I'm just writing F as m times I hat plus n of j hat across C is, you end up integrating m dy minus n dx over c as a vector line integral from earlier in the section. If you prefer different notation, this would be integrating the vector field negative n comma m dot dr. Okay, so this is our method, this is our formula to actually compute flux. So computing flux turns out, it's very similar to things that we've done before. It just is a slightly different. For f, you start off f as m comma n, and you rewrite it in this form. So here, let's take a look here. Find the flux of f is equal to 2x I hat plus x minus y j hat across the circle. R of t is cosine t I hat plus sine of t j hat, where t runs from 0 to 2 pi. Okay, this is a counterclockwise oriented circle that goes around exactly once. Here our m is 2x, and our n is x minus y. So what we have here is that our flux is equal to the integral of m dy, so that's 2x dy, minus x minus y dx. Okay, so now we need to fill in everything in terms of our parametrization. So x will be cosine t, y will be sine t, dy will be cosine t dt from y is sine t, dx will be negative sine t dt. And so this is the integral where t runs from 0 to 2 pi of 2x dx minus x minus y dy. Okay, so this is our calculation here. If I haven't botched anything up here. And so this is a relatively straightforward trigonometric integral. I'm going to skip the details. And so you end up with pi. So pi is positive. So that means the net flow, the net flux, is outward. So here's our circle. There's some fluid flow here. There's more that is leaving the circle than is entering the circle for this vector field right here. Whatever it represents, we don't know what it represents. There's more flux flowing out than entering.